Welcome back. Let us resume our discussion on the ICMR and look into the solutions which can be taken to get a full rail to rail ICMR. One of the ways, of course, that may seem obvious is that if we have the option of choosing a 0 VT transistor for the NMOS, we can increase ICMR. If I have the option of very low VT transistors, I can select those specific devices to reduce the VCM min. And in some technologies, even for 180 nanometer TSMC or UMC models, you may have transistors which are having lower VT, and I can choose those transistors in some cases to have to increase the signal swing. Not all models, not all foundries provide those models. In some cases where you have those models available, if you have access to those particular device models, you can use them in improving some of the device performance. So, in this case, we can probably go for a 0 VT transistor for the NMOS for improving the ICMR on the lower side. So, in that case, of course, as we see the for the ICMR min, the VT1 will be reduced few tens of millivolts, and as a result you will have VCM min going towards lower value. If we do that, we also, if you look at this equation here, the VCM max also depends upon VDD minus the VSG of the PMOS, and we say that this is the gate voltage VDD minus VSG. This is going to be the gate voltage of the PMOS. This plus VT1 is the maximum input voltage that you can have. This is the maximum input common mode. Now, if VT1 is 0, then of course, I have the maximum input common mode given by VDD minus this quantity. You do not have any longer the V over drive coming, but you have VDD minus this entire VSG term coming. And therefore, once again, if I really want to take the advantage of 0 VT NMOS, I would like to get rid of this VT also. So, we can go for VT n tending to 0 or low VT NMOS, also VT mod VTP tending to 0. If you have low VT PMOS option, then only you will be getting the same advantage on the upper side. If you take the nominal VT PMOS, then the upper side you will be having limitation on the ICMR. So, make sure that if you are choosing low VT NMOS, you should also choose a low VT PMOS. That is one way, and of course, in case you do not have that option available, we can go for some other techniques to improve the overall ICMR. We can go for architecture level choices. We can combine, say, two different kinds of comparators to arrive at a overall scheme where you have full range ICMR. So, let us have a look into that, and let us try to address the issues related to that scheme. So, here I can, if I take note of the fact that an NMOS comparator is going to have an ICMR which is limited on the lower side, because for the NMOS I have the VCM min getting limited by the VT of the NMOS transistor. On the upper side, however, we can go all the way very close to VDD if I am choosing nominal VT transistor. So, for the PMOS input device, the condition is just reverse. So, for the PMOS input device, the input can go all the way to ground, the ICMR can go all the way to ground, but on the upper side it is limited, you cannot go very close to VDD. So, the input common mode range is limited on the upper side in that case and in the lower. So, if we have a scheme where we are just combining the comparator with PMOS input device and a comparator with NMOS input device, and then trying to combine their output in a correct fashion using a multiplexer. We can have an analog multiplexer which is having a select line over here. This is an analog multiplexer. So, we have to choose between the inputs of the CP and CN. So, we have the same V in, sampled V in going to both of them, and you have the same Vref also going to both of them. So, this is your ramping Vref which is coming from the ramping circuitry, and this is the sampled V in. So, this is common to both. All I need to do is choose one of them depending upon the input magnitude. Remember, if the input magnitude is larger, the NCN will perform properly. However, if it is going lower, it will fail. However, the CP will perform properly. So, I can basically compare this V in using another comparator with the mid value of the IC, mid supply value, which is VDD by 2, and if the input signal is higher than VDD by 2, we know that the Cn can work well. So, this can become our select signal. Let us ignore this, and I can put the option 1 over here and 0 over here. 1 over here means when the select signal over here, if I call it select signal, if the select signal is high, the one input will be selected, that means the Cn will be selected. So, if the input signal is the input signal is higher than VDD by 2, then I would like to select the Cn. So, I have just put a bubble over here, that means is having inversion. So, that means just to follow the sign, if the input signal is higher than VDD by 2, that means this will be going low, because I have put a bubble over here, and that would mean that this will be 1 when the input is going higher than VDD by 2, and that will be selecting the Cn, and likewise in the other direction will be selecting Cp. And such an analog mux can be implemented using a simple transmission gauge that we have discussed in the last class. So, you can have the Tg where you have the V, the two inputs of the Tgs coming from the Cn1, the Cn and the Cp, and the outputs being combined over here. And here you can of course have the select lines, you can have the select and select bar over here. So, when the select is high, I can select the Cn, and vice versa, I can have the select bar over here, and this is my output. So, this is an analog mux, and we have discussed that the on resistance of the switches can be relatively very low, and as a result, whenever one of these muxes are on, the corresponding output Cp or Cn will be connected to the output. It is expected that Cp and Cn are digital values because they are comparator outputs, and therefore, these are going to be full swing signals close to either VDD or ground, and we know that the Tg will be able to pass both of these. So, this is one scheme where we can apply a Tg based mux to select one of these comparators based on the input signal level. Now, one of the question is that we pointed out that the Cp works for input signal levels, which is say higher than VDD by 2 going all the way to is going to work all the signal levels from going all the way to ground, and Cn works for all the signal levels going all the way to VDD, but it does not work for the signal levels going all the way to ground. So, what to choose over here? Is the choice of this comparator important? The choice of input device, whether you are going to use N or P, is it important for this one? Here, of course, we saw that it is critical. We are choosing these two for different ranges of input operation. However, here we are assuming that this is working for the entire range. So, is this an issue? So, this was in fact one of the questions that was raised in our discussion, offline discussions, and the reason why we are not concerned about the type of input device over here is that the reference voltage is fixed, it is just VDD by 2, and therefore, the comparison operation over here or high gain operation of this amplifier will be of concern only in the vicinity of VDD by 2. If the input is much higher than VDD by 2, definitely the output will be deterministic. If it is much lower than VDD by 2, also again it will be deterministic. So, the critical point for this comparator is only when the input signal is close to VDD by 2, and for that, whether it is NMOS or PMOS input device, it does not matter, both of them are going to work well if the input device if the reference signal is VDD by 2, whereas for the other two, what is happening, reference is being swept, and the critical point of concern is when the input signal is close to the reference. Therefore, for the entire range of reference 0 to VDD, and hence corresponding to that entire range of the input signal should be able to work. So, for that the operation is the high gain operation is happening in the common mode fashion, because there the input signal and the Vref are very close at the flip point where the comparator is changing the result, changing the output, and hence for these two we have to be concerned about the input common mode range. However, for this we do not have to be, and therefore, the choice of input device is not critical. Another thing is what about the gain specification. So, for these comparators anyway we have the specification of the gain. For here, once again, is gain critical? The answer would be no, because if the gain is poor, then the resolution of this comparator will be poor. That would mean that for the V in close to VDD by 2, say VDD by 2 plus say delta. For a sufficiently large delta, the result is not well defined. It can be either high or low, and this delta can be few tens of millivolt. It can be also 100 millivolt. In this case, we try to keep this delta small, whether governed by the resolution requirement. There we try to set the delta within 15 millivolt, which is coming ultimately from our requirement of the quantization and the accuracy of the AD, the precision of the ADC and so on. But here that delta is not a concern. Why? Because even if the gain is poor, and as a result the decision in a relatively wider range is non-deterministic, even there is a 100 millivolt range where the gain or the response is undeterministic. There the choice of Cn and Cp in the vicinity of VDD by 2 will not be so critical, because if your V in is VDD by 2 plus 100 millivolt or VDD by 2 minus 100 millivolt, still these comparators, both of these comparators can work. So, in that range it is not very critical to choose one of them. Only when the input signal is far away from VDD by 2 going towards ground or going towards VDD, which is basically 0 plus Vt, and on the upper side VDD minus mod Vt. So, those are the if the input signal is beyond these two range, this upper limit of VDD minus mod Vt and the other side mod Vt n on the lower side. So, if the input signal is going above and below this range, then only the selection of these two becomes critical. We have to make the right selection. However, within plus minus 100 millivolt, if one of them is getting selected and the other one is not selected, that does not matter, because both of them are going to operate well. So, therefore, the gain requirement for this comparator is not so critical. I can have a poor gain result with just maybe 10 or 20 gain, that is also going to be good enough for this particular comparator. So, if you have a 20 gain, difference of 100 millivolt will be amplified to full VDD swing. Therefore, this is relatively going to be a cheap comparator. We do not need to worry about the gain, high gain requirement for this one. Of course, bandwidth should be fast enough. It should be able to respond fast, so that the comparators are getting selected at the right time. So, speed should be enough. Gain requirement is relatively poor. Still, to be safe, if it is not hurting our power requirement, we can still go for a gain which is at least say around 100, unless it is significantly hurting our power budget. And if we look at some results coming from simulations, the power budget for these transistors, these comparators will be within few micro amperes, close to 10 microampere within that. And if we are having significantly lower gain requirement for this one, the power once again can be lower, and bias current can be sacrificed. It can be a fraction of microampere, and still it can meet the required nominal gain. You just make sure that the gain is sufficient. In the worst case, it does not drop below the required value. So, this is going to be a relatively cheaper device as compared to the other two. So, this is another way in which we can achieve full ICMR without sacrificing the overall performance, without having stringent dependency on the input device sizing of the comparator that we just discussed. Another very important issue that we would like to mention is the choice of single stage versus two stage, and interfacing of comparator and the digital component which are going to follow the comparator. So, these two issues are related and going to play a very important role in designs where we are having final interface between an analog comparator and the subsequent digital unit. So, let us look into this. So, we have seen that our ultimate target is around 400 gain from the overall comparator, and also bandwidth requirement is around, if I look at it, 1 megahertz. In your earlier examples, while working on front end amplifier, we have obtained this amount of gain from a single stage itself. But of course, in that case, the bandwidth for the single stage will also get limited. If you try to obtain this entire gain from a single stage, the bandwidth also gets limited. But despite that, if you suppose you are trying to get this gain from a single stage unit and trying to just apply the first differential stage for the comparator operation, and trying to interface the comparator with the next stage, which can be just a digital inverter, for example, the simplest digital circuitry. So, if I do away with the second stage, what are the pros and cons? This is quite an important issue to be addressed and understood. So, here if I look at the interface between this differential amplifier and the inverter, assuming that this is able to achieve a sufficient gain, and as a result the swing over here is sufficiently large, we are expecting that this inverter will be able to convert this swing into full digital swing, because this is able to achieve a overall 400 gain, and therefore, a small difference in voltage of course here, maybe just 2-3 millivolts of difference between these two signals is going to give me a close to a full swing at this point. So, in that case, I may not even require the second stage and may be able to get the entire gain from this stage. There we have two cases. If you are depending upon this GM RO product of this first stage in order to obtain the overall swing, there either you can have a larger GM or you can have relatively large RO to obtain that while meeting the bandwidth constraint. Case 1, if you have large GM. So, if you have large GM, that means the current GM, the difference in the overall current that you get, assuming small signal operation, delta ID, that is say ID 1 minus ID 2 overall, that is going to be proportional to GM times delta V in, and therefore, for a given delta V in, if the GM is large, you will be able to switch the current completely into one of the devices for a relatively small V in. And if your GM is sufficiently large, so that for the required delta V that we have estimated is at 15 millivolt, the signal is completely able to switch, or the current is completely able to switch in one direction. That was definitely turn off one of the devices, and as a result we can expect full swing at this point. For example, if this device is getting turned off because a large GM I in getting diverted completely and this is getting turned off, what will happen? This is anyway going to be VDD because there is no path for the current to flow. This will be VDD. Otherwise, in the other case, if this is turning off, in that case once again there is no current path in this one, and therefore, this is going to be close to VDD, this is turned off, and as a result there is no current from the PMOS at this point, whereas this is completely on. Therefore, this will be discharged to ground. So, in either of the two cases, if GM is sufficiently large, this node will be going to completely VDD or ground for the given delta V in, and therefore, we may not even need the second stage, and we can just put another inverter and go to the digital domain. However, if the GM is not sufficiently large, the current will not be switching completely, although you may be having expected you will be having a expectedly large gain and expecting a large signal swing over here, but if the current is not switching completely, ultimately for increasing swing, since the current is not completely switched and none of these devices are completely off, one of the devices will be entering into triode region. For example, if the voltage over here is larger, here it is smaller, and ultimately this voltage is dropping down, this is increasing. This transistor is going to remain in saturation, no problem, but if this is dropping while this transistor is remaining on, this will ultimately enter into triode region and further gain will be dropped. And once this transistor enters into triode region, the gain of the overall amplifier circuit drops and it will no longer go down further, and it will saturate to a value which is higher than ground. It can be almost close to VDD by 2 also, if the transistor is not, if the sizing is not proper. So, it can hang midway, rather than going all the way to ground, it can be close to VDD by 2 because the gain has dropped while this node is going to go down. Therefore, on the upper side also similarly, if the signal over here is larger and here it is smaller, once again if this transistor is trying to go, if this voltage is trying to go up while the current is not switched completely, this transistor may finally enter into triode region because of the signal going up, and as a result once again gain will drop, and once again the voltage may not be able to reach VDD. So, therefore, the swing can get limited because the current is not getting switched completely and the gain is dropping before the signal reaches full swing, and hence it can be risky. I mean, you are not having full swing over here and then you are connecting an inverter, a digital inverter over here to this analog signal. So, if we have say a signal which is hanging midway, say close to VDD by 2 in that vicinity, and we are applying a digital inverter directly over here, what can be the condition? None of the NMOS or PMOS will be completely off, both of them will be remaining on, especially if it is close to say VDD by 2. Under this condition, both NMOS and PMOS are having sufficient VSG, you are having sufficient overdrive voltages. As a result, you can have a huge amount of static current flowing through this inverter for that duration. So, as a result you will end up burning a good amount of static current for that small period. For the comparator, we have control on the current. By using this bias current, we can control the total static current over here. CMOS inverter, we do not have current control. So, it just depends on the W by L and the VGS. If the VGS is sufficiently strong as compared to VT, you have sufficient V over drive, it will burn a good amount of static current, and within a small period it can give you a huge amount of current dissipation, and it can disturb your power balance that you are trying to create. So, that is one issue. Another and it can have cascading effect. So, you can have the next stage also, if this is not having full swing, is somewhere close to VDD by 2, the output of this inverter will also be not having full swing, and subsequent stage can also burn more power. In general, the characteristics of the inverter is, of course, if you are having the transition region gain on the inverter which is sufficiently large, and your signal is close to say midway in this transition region, even if it is not exactly VDD by 2 and the slope is large, you can ensure that if my input is say slightly higher than VDD by 2, the output will be relatively sufficiently lower than VDD by 2 if the gain is large. The slope is large and my input is little bit at least lower than VDD by 2, this larger slope will ensure that the output is sufficiently lower. So, definitely that will help in pushing the output of this inverter further away from VDD by 2. So, that is the property of an inverter, regenerative property, where if you are having input which is at least little bit offset from the trip point of the inverter, not necessarily VDD by 2, the trip point of the inverter, we can make sure that the output of the inverter is sufficiently further away from the trip point. But in that case also we can end up burning a good amount of static current. So, that is not a good practice. So, although you may be able to meet your gain requirement from the first stage, it would be good to involve or introduce a second stage, so that it is ensuring almost full swing, and it is ensuring that either the output is going all the way close to VDD or ground. So, that the interface between the comparator and the digital inverter is robust enough, it is not leading to static power dissipation in the inverter. Another critical issue will be the trip point of the inverter that I just mentioned. Trip point is not necessarily VDD by 2. It is not necessary that this midpoint that we are looking at in this transfer characteristic is going to be VDD by 2, and that is another important issue which plays an important role whenever we are interfacing an analog unit like a comparator output with a digital inverter. So, let us look into the concept of trip point in a little bit more detail after a short break. Before we go there, we can see if there is any question. Any question, any part needs discussion over here? Yes. Okay, so let us resume our discussion. Any question regarding the discussion we had so far regarding the mask based selection? All right. So, let us look into the concept of trip point of the inverter, which is again going to play an important role for the analog circuits wherever you are trying to incorporate digital inverters interfaced with analog signals. So, trip point is defined as the threshold of the inverter. This is the input level for which output is equal to input. So, if I okay, if I draw the transfer characteristics of an inverter and look at the V out equal to V in curve, which is 45 degree, the point where it intersects is going to be a trip point, the point at which V in is equal to V out. This is V out and this is the V in. So, if you are going for V in higher than this trip point, we are expecting that again you are having the output going down, and on the upper side once again output going close to the VDD. And this trip point can be seen as the threshold of the inverter, the point at which it is going to the input value at which it is going to switch from high to low. For example, if you have trip point which is higher, we expect that this curve will be moving further over here, and therefore, this is the value of V in for which it will be switching down. Likewise, if the trip point of the inverter is lower, we will expect that this is the value, this is the value of V in, this is the value of V in 2 for which the inverter is going to switch down. So, we can see that the definition of trip point is going to tell us what is the minimum value of V in for which the high to low transition in the inverter will take, or corresponding to that the low to high transition of the inverter will take depending upon the input signal. So, this trip point of course tells me that what is the effective threshold of the inverter. Just like the MOSFET has a threshold, we can say that the inverter has a switching threshold, and it depends upon the intersection of this V in equal to V out curve and the inverter characteristics over here. In order to obtain this trip point and see what are the parameters on which it will depend, we can write down the equation for the current in the inverter when the trip point is occurring. So, when the trip point occurs, we are assuming that both its input and output voltages are close, and they are somewhere midway, they are not close to extremes. So, if I take that assumption for the time being, then I can say that this is close to say VDD by 2, and I have V in and V out approximately equal to V in. This is VDD and this is ground 0. In that condition, what is the region of operation for the PMOS and NMOS? If I assume that say this is close to VDD by 2, suppose I am taking the middle curve and I assume that this is close to VDD by 2. So, both of them V in equal to V out are going to be close to VDD by 2. As a result, we can definitely see that for the NMOS, the gate voltage, drain voltage similar. As a result, of course, this is going to be in saturation. Likewise, for the PMOS, the same thing, gate voltage, drain voltage similar, therefore, is in saturation. Therefore, at that trip point, both the transistors we can assume they are in saturation, and I can write down the current equation for both of them, IDN equal to IDP for the trip point. And for IDN, if I write this as say root K, let me write down the equation as Kn Vgs minus Vt square. So, this is V in minus Vtn square, and this is equal to the MOS current, PMOS current, which is equal to Vsg minus mod Vt square. So, the Vsg is VDD minus S, which is minus G, which is your V in once again, minus mod Vtp. So, I can equate these two. I can take the root Kn V in minus Vtn equal to, I am ignoring the channel length modulation for simplicity. Of course, that will also come into picture and influence these voltages. And from here, I can find out the V in. If I take the Kn upon Kp over here, I have the Kn upon Kp, and you have sorry, this plus 1 coming over here, and this is going to be VDD plus mod plus Vtn times Kn upon Kp minus mod Vtp, and as a result I can write down the particular trip point value as VDD plus Vtn Kn upon Kp minus mod Vtp upon root under once again Kn upon Kp plus 1. So, we can see the dependencies over here, how they are coming up. So, Kn Kp is equal to the transconductance parameter of the MOSFET, which is equal to mu n Cux W by L. So, if I assume mu and Cux are constant, so these two quantities are ultimately depending upon the W by L ratios. And if I look at older technologies, even in 180 nanometer Kn upon Kp ratio, if I talk about the mu n upon mu p ratio, that is around 2. So, NMOS is faster, or the mobility of the NMOS is slightly higher as compared to PMOS by a factor of 2 to 2.5, and as a result if I assume the W by L's are similar, this will have that particular factor of nu n upon mu p coming in. Now, if I look at the design parameters, that is the W by L available to us, there we can see that if I am increasing the k n upon k p term, and if I assume that these terms are getting cancelled out almost similar, and therefore, the magnitude over here is relatively lower. If I just increase the k n upon k p term, this denominator term is going to increase, and as a result, if I see the trip point is going to shift towards lower value. So, in that case, I am having the overall trip point shifting towards the lower value, and hence the threshold of the inverter or the trip point of the inverter is shifting towards lower value. Likewise, if I am having k n upon k p lower, that is I am increasing the W by L of p and reducing the W by L of n, the trip point will be shifting towards relatively higher values. What is the consequence of that? It means that the overall trip point is going to be determined by the W by L ratios and also the Vt and Vtn values, Vtn and Vtp values, which are not very much in designer's control. They can vary from device to device significantly. So, even if the k and kp are set almost equal, the Vt and Vtp value may not be exactly same, and likewise you are having in the denominator, especially you have the k n upon kp ratio, which can vary from unity. So, once again you are having the other parameters also, like the lambdas, which we have ignored, coming into picture and determining the overall trip point. So, that we have ignored for simplicity, but ultimately lambdas are also going to play a role. Therefore, the trip point is dependent upon the sizing of these devices and also the terms like threshold voltages and the lambda, and therefore, they are very much process dependent and can vary from inverter to inverter. Even if you have inverters with the same dimension, they can have significantly different trip points. It can vary by several tens of volts, it can vary by hundreds of millivolts, and typically in the CMOS process you can have the threshold voltages of NMOS getting higher uniformly. That in that case, all the PMOS transistors on the die will be having slightly higher voltage than the nominal case. You can also have a condition where the NMOS threshold voltages are going high. So, in that case, once again all the NMOS transistors on the die will be having slightly lower threshold or higher or threshold voltage than the nominal value. So, both these scenarios can happen. NMOS or PMOS can have uniformly relatively higher or lower threshold voltages. So, we call them process corners. So, basically we have 4 possible process corners. You have the case where you can have the NMOS, you can have so, if I denote one of the axes for the PMOS and another one for NMOS, you can have a case where both NMOS and PMOS are slow. That means, both the threshold voltages of NMOS and PMOS for all the devices are higher than nominal. That means, the on current will be smaller, and hence the speed will be smaller. You can have the condition where both the NMOS and PMOS threshold voltages are lower than the nominal. In that case, both the devices will be faster than expected, because the threshold voltages will be smaller, on current will be faster. So, you have the fast corner. Likewise, you can have the other 2 corners where you have slow fast, one of them having relatively smaller threshold voltage than the higher other one, and you have the fast slow corner. So, you can have in general these 4 corners, and that would mean that dominantly on an average, if you take an NMOS, if the device is in slow fast corner or the die that you are having is in slow fast corner, that means the NMOS will be relatively slower as expected, or the threshold voltage of the NMOS is higher than expected, and vice versa. So, in general we can have these 4 corners, and as a result the threshold voltage of the MOSFET or the inverter that you are expecting can significantly vary from what you have designed it for in the simulation. And hence, when we are targeting interfacing of an analog signal with the digital inverter, we can not be sure that the threshold voltage or the trip point of this inverter will be VDD by 2. It can vary significantly, and in that case the assumption that a given swing, say from 1.6 volt to say 0.9 volt, it will be reliably amplified by this inverter and converted into a digital level, because the trip point has been set to be midway between these two. That is not going to work. So, in a simulation you may be getting some values like this, and minimum value over here 0.9 and maximum 0.6, and by sizing the W by L of these two, for example, as I said, if you increase the W by L of the PMOS, the trip point will shift further. It will be further higher over here. The characteristics will be shifted further, as we just saw. So, if you do that, then we cannot expect that whatever trip point we have designed it for, say midway between 1.6 and 1.9, after the fabrication the trip point will remain there. It can go down also, it can go down below below 0.9 also. Therefore, it will fail in that condition. So, this is not a very robust case when you are trying to interface the analog output coming from the comparator directly with the digital inverter. So, it will be better to convert this signal into full swing using another stage and then apply to the inverter. So, that will lead to a more robust design, and it will not be dependent upon process. It will not be dependent upon the sizing of this W by L of P and N, VT of this P and N. So, that even you are having changes in the process corner, you are having different corners because of which the threshold voltages are changing for the NMOS PMOS pair, and as a result the trip point of this inverter is changing. Still you will be ensuring that the output signal is going all the way to VDD and ground, and hence the inverter is going to work reliably. So, this justifies the use of the second stage, even if in case you are having a lower gain requirement and you are able to do it with a single stage. More reliable design would include a second stage, so that you are always ensuring full swing before it goes to the comparator, before it interfaces with the digital inverter. So, we saw two reasons. One is the static power dissipation, so that when the signal is close to VDD by 2, not fully ground or VDD, it can lead to a lot of static power dissipation in the interfacing inverter. Second reason is the robustness of the circuit, where we are talking about the trip point of the inverter, which can vary significantly. It is not necessarily VDD by 2, as we see. It depends upon the device parameters and the W by L ratio of the NMOS and PMOS transistors, and that can also significantly vary over process. It can be very different from the expected value, and hence such an interfacing will not be very reliable. For this particular stage, the gain will not drop unless this output voltage is reaching all the way to VDD minus V over drive. So, if the V over drive is small, it can go all the way to VDD. Till that point also the gain will be sufficient. Likewise, on the lower side also the gain will not drop unless the voltage over here has gone down all the way to V over drive of N, and that would mean that few tens of millivolts. So, if you are sizing this properly, the V over drive of this NMOS can be within few tens of maybe just few tens of millivolt. As a result, the gain of this stage will not drop, or this NMOS or PMOS will not enter into triode region. Even if the voltage is over here is going all the way to VDD minus V over drive, which can be very close to VDD, or this voltage is going down all the way to just V over drive of N, which is once again very close to ground. So, you have few tens of millivolt, maybe 50 millivolt over here and 50 millivolt over here. Even for this entire range, these two transistors are still in saturation, therefore gain is maintained. They will not this swing will not reduce the gain of this stage and then create problem in the amplification. Whereas in this case, what is happening, if the GM is not sufficient and the swing is increasing, the transistors are entering into triode, and as a result the gain is dropping and is not able to approach VDD or ground, because before it can approach VDD or ground, the gain of the circuit has dropped and it stuck to that intermediate value, and in that case interfacing it with the digital inverter is going to be a bad idea. Whereas in the second stage, you have the opportunity of having full swing, because this transistor will not enter into triode even if this voltage approaches all the way to VDD, all the way to ground. That is the reason why interfacing this with the differential amplifier, then applying a digital inverter, will be a better option, a more robust option from the point of view of process variation and also power dissipation. Any question? Any question before we proceed further and look into some other design issues associated with our comparator? So, we should have clear information regarding the trip point. Once again, if I look at the trip point, we can if I am talking about the W by L ratio, it is also important to intuitively see what is happening if I am changing the W by L of N and P. So, at this point, I see that means if I am having the Kn and Kp ratio increasing, then that means that the trip point is going to go lower. Why it is happening, that also we can see. So, if the W by L of NMOS is getting increased, that means for a let me draw it on a separate plot so that it is more evident. So having this intuition is important whenever we are looking at the sizing of the inverter which is interfaced with analog circuitry, so that we are clear about the W by L sizing requirements. So in many cases it comes into picture when we are looking at designs having mixed signal component. So if I say that I am going to increase the W by L of the NMOS, then what do we expect should happen to the transfer characteristics? This equation tells me that the transfer characteristics should shift towards the left, because the Kn upon Kp ratio will try to bring this value down, trip point down. Now if I look at what is happening here, if I am having the suppose this is my original curve where the trip point was given by, say, VTH1, which is trip point of the inverter, threshold voltage of the inverter, and then I decided to increase the W by L of this MOSFET. That means for the same VTH, since the W by L has increased, I would expect larger current in the NMOS. That means NMOS has become stronger. I have put larger W by L for the NMOS. That's why for the same VTH I would expect larger current over here. On the other hand, we have the same W by L for the PMOS. Therefore, the VSG of the PMOS is remaining same. W by L of the PMOS is remaining same. This is remaining same, but I have increased the W by L of N as compared to the original device where the trip point was obtained here. So now here, if I see that the VSG of the MOSFET is remaining, PMOS is remaining same, and the W by L is remaining same, and for the NMOS, however, the scenario is different. W by L has increased. For the same VG, therefore, I would expect larger current flow over here, and that would mandate that the PMOS also has larger current, because they are the same device, and the only way PMOS can have larger current, this voltage should go down, right? That would mean that this voltage must be further down as compared to the previous values. You can see that this curve should shift down from here to here. So we say that the pull down device is becoming stronger. If the pull down device is becoming stronger, it will be able to pull down the inverter from high to low for smaller voltages. The threshold voltage become lower. So the NMOS is a pull down device. It tries to pull down the output to ground all the way. Whatever capacitance over here is appearing because of the parasitics, it will try to discharge it to the ground. So if the NMOS is becoming stronger, the device over here is becoming larger, that means it can pull down the device for a smaller input voltage. On the other hand, if the PMOS is becoming stronger, it will take much larger voltage over here to pull down the device. So the characteristics will shift towards the higher side. So this is important to keep in mind. Increasing the W by L of the NMOS, that means we are making the pull down device stronger, that will pull down the inverter characteristics earlier for a lower input voltage. Whereas the pull up device, the PMOS, if I am trying to make that strong, it will take a larger input voltage to pull it down, because the pull up device has become stronger. So this is the direction in which my Kn is increasing, or in other words, W by L of N is increasing. Or you can say the ratio of these two quantities, W by L of N and W by L of P. So if I am making the W by L of N stronger as compared to W by L of P, then this is the shift in the characteristic that I can obtain. This is very important, and whenever we are dealing with interfacing of inverters with analog circuitry, this sizing constraint needs to be addressed. In some cases, we would like to intentionally keep the VTH on the higher side or on the lower side. And remember, the threshold voltage variation, it reduces if the size of the MOSFETs are larger. So I will very shortly discuss the concept of offset. So if the MOSFET devices are larger, the sigma VT, the distribution of the VT becomes sharper. So sigma of the VT drops with the area of the MOSFET. That means if I collect, say, 100 MOSFETs of dimension W by L, so their dimension, the product is W and L1, the area is W1, L1. So they will have a certain distribution of VT. That means this is the VT that I am measuring, and this is the number of samples. So I am taking first 100 MOSFETs with having W1, L1 dimensions. Their area, therefore the gate area is W1, L1. If I look at their VT distribution, some MOSFET is n number of MOSFETs are having a VT which is over here. Another given number of MOSFETs are having VT which is over here. Some MOSFETs are having VT which is higher than the nominal. This is a nominal VT that I expect, and along that you have a Gaussian distribution. If I take another 100 MOSFETs which is having the W by L, say 4 times, in that case the distribution or the sigma of the distribution also becomes sharper and the distribution becomes smaller. That means the spread in the VT becomes smaller. Why? Because one of the important contributor to this sigma Vt happens to be the dopant fluctuation. When the MOSFET size is smaller, in the channel you have, under the channel you have some dopant which are constituting the channel, and they are basically determining the threshold voltage, and those dopant numbers are ultimately going to vary from device to device. If you look at, say, different devices of different dimensions, you can have the dopant numbers varying very significantly, especially if it is scale device. And as a result, the threshold voltage, which is dependent upon the dopant, that can also vary if the number of dopant is fluctuating. If we have larger devices, then the percentage variation of the dopants is also smaller. If we have a device area which is larger, a much larger device, then the percentage variation in the dopant will be smaller, because if you are having a very small device for a particular technology, minimum size device, then the number of dopants is countable, and the percentage fluctuation that you can get over here will be larger. As you are going on increasing the area, the percentage fluctuation that you get in the number of dopants over here also reduces with area, because here the probability of finding electrons per unit area is given, and then you have a small area, therefore the probability of fluctuation over here is much larger, whereas the probability of electrons per unit area multiplied by this larger area, so you are having a much larger area over which you are averaging the probabilities, and as a result you are having the percentage variation in the absolute number of dopants over here relatively smaller. As a result, larger number or larger area of the device, larger WL, leads to smaller sigma Vt. This can be analytically derived also from the MOSFET threshold voltage equation. If I assume certain dependence of the threshold voltage on the dopant, so random dopant distribution, or RDF, is one of the major contributor to this threshold voltage mismatch or variation from device to device. And if I keep this information in mind, from circuit point of view, it can be very important, because if I increase the W by L of the MOSFET, the threshold voltage distribution can be relatively smaller. I can expect that the threshold voltage of the MOSFET will be close to the nominal value. It will not deviate too much. Whereas if you use minimum size transistor, the variation can be big. If you use minimum size transistor, the distribution can be much larger, and the nominal Vt is say 0.4 volt. The Vt can go all the way to say 0.2 volt. 0.6 volt, it can go all the way to say 0.2 volt. It can be bad if you are using minimum size transistor. So I'm being a little aggressive over here, but even in good technologies you can have at least 100 millivolt plus minus variation for a minimum device. Whereas if you are having say larger devices, the distribution becomes sharper because the sigma Vt reduces. So a larger device, W by L, larger W and L of the PMOS or NMOS will ensure that the Vt of the device is close to the nominal value, and then I can have more assurance regarding the threshold voltage of this inverter, or the mismatch between the transistors can be relatively lesser. So I can be more deterministic that okay, if I am choosing a certain W by L ratio for this, my V in, or the threshold voltage or the trip point of the inverter, can be more deterministically obtained from this equation, because these are not varying so much. This distribution or the variation of these two components is not so much. So that is another important point to be taken care of. While looking at the analog circuits, the differential amplifier, or the operational amplifiers mismatch and offset, once again this point has to be considered. Let us take a break and see whether we have any question at this point before we can resume our discussion.